Both of them lift airplanes into the skies, both spin a propeller, both roar loud, and both are icons of the industrial era. These two burning hearts gave us the chance to touch the sky, the piston engine and the turboprop engine. Hello aviators, Sky here, and today we'll get to know two types of aircraft power plants and we'll try to understand, if they are so similar, why are they so different? The first hero we'll meet today is the master of harmonious roles of pistons and cylinders. A piston aircraft engine is basically an internal combustion engine, where the thermal energy of the expanding gas, generated by an ignition of fuel inside the cylinders, makes the pistons move. These in turn rotate the engine shaft, and consequently the propeller. In general terms, it is a variation of the classic piston engine, so common to most means of transport. In fact, what we find under the hoods of most cars are basically members of this family of engines. For quite a long time, piston engines had become the basis of aviation, from the simplest plane flown by the Wright brothers to the monsters of the dawn of World War II. But in the end of the 1940s, a new voice tapped into the melodic chanting of the pistons. The gas turbine engines started to sing. The turboprop aircraft engine is a representative of the gas turbine family of engines, which also includes the most widespread power plants of the heavy civil and military aviation, the jet engines. In a jet engine, air is sucked in and compressed by several rows of fans in a compressor before being mixed with fuel, ignited, and exhausted backwards at an insane speed. During the entire process, this air also spins the shaft, along with the turbine and the compressor. Unlike the jet engines, which push the plane forward by exhausting gas at an extreme speed in the opposite direction, the turboprop engines use this operating principle only partly. The most important thing for these engines is precisely the rotation of the shaft, as it not only makes the compressor work, but also moves a huge propeller, which in this case is the main driving force for the airplane as it flies. As we can see, piston and turboprop engines are completely different in terms of operating principles, and basically there's just one trait that they share, the propeller that both of them spin around. This brings up an obvious question. If everything comes down to spinning the propeller, who cares what the engines do under the hoods to make this happen? Actually, this question can sometimes become a problem for the marketers of aviation companies. Let's take for example the Piper M350 with a piston engine. It costs about $1.5 million. And here we have its M500 brother with a turboprop engine, which seems to be the same but costs $2.2 million. If they are practically identical, why pay more? Is this some sort of a marketing trick meant to drive up the price, or is there a difference after all? The reality is that although the operating principles of these engines are not in plain sight for a layman, they actually do bring about tons of nuances into every aspect of their actual use, from manufacturing and maintenance processes to performance and operation. I'll note straight away that the amount of these nuances is enormous, and each of them can be a topic of epic debates between the fans of pistons and turbines. Meanwhile, we will try to analyze the most important differences. Since we have already mentioned the price differences between planes with different engines, let's try to give an answer to the question for the turboprop. Why so expensive? At first glance, turboprop engines have a rather simple overall design. Several rotating fans, a combustion chamber, a turbine. This can lead to the conclusion that they should be cheaper than the huge pile of mechanisms we see in a piston engine. However, gas turbine power plants generate within themselves, let's say, a highly aggressive environment, where extreme pressure is combined with temperatures and speeds that are just as extreme. This is why seemingly simple components are made of highly complex materials and alloys, with top manufacturing quality at all stages, none of which comes cheap. On the other hand, in spite of featuring a vast amount of mechanisms, piston engines are usually cheaper due to less demanding manufacturing process and lower grade materials. Besides, many of these components are used not only in aviation, which reduces their cost even further. This leads to a striking difference in their prices. While the engines of many piston aircraft can cost about $100,000, even the similar in terms of performance turboprops can cost several times more and can easily top $1 million. This leads to a contrasting division of the aviation market. A significant part of general aviation consists of rather cheap machines, which cannot afford expensive technology. After all, no one's gonna fit a $500,000 aircraft with an engine that costs an additional $500,000. And if that's the case, what's the point of paying that extra money? Let's find out. What about reliability? Here the turboprop is the top dog. While its manufacturing and materials are expensive, the overall design, as we know, remains quite minimalistic. In normal operating modes, all elements are experiencing quite a stable dynamics, which basically consists in a rotation at a constant speed. In addition to that, most of the elements don't dynamically contact each other, which would otherwise be causing friction. Plus, with the proper balancing, there won't be much vibration. All this translates to high reliability and a long life cycle. The turboprop engine is considerably superior to the piston engine in terms of durability, and its time between overhauls is exponentially longer. It can be run very actively for a very long time, which for instance is important for commercial airlines, where the aircraft spend many hours in the skies every day. But there is yet another but. Due to the high energy processes that take place within the turboprop engine, there is a very important nuance to it. It is quite demanding in terms of operational conditions and has some strict limitations which should really not be broken. This is why many machines with turboprop engines are fitted with all sorts of automatics, which can be generalized as FEDEC, or Full Authority Digital Engine Control. A computer takes care of monitoring and regulating the engine to keep it within the permitted parameters. In addition to that, it makes the work of the pilots easier and increases safety, like a kind of an automatic transmission. It all sounds great, but we need to realize that FEDEC is a complex and rather expensive system, which also increases the overall price of the aircraft. And if something happens, what does it take to repair those engines? A ton of money. Due to their complexity and high precision manufacturing of their components, the repairs require highly qualified personnel, special equipment, and spare parts. Even the apparently insignificant defects can be a cause of a failure. In fact, in field conditions, it is easier to simply swap the entire engine and send it out to be repaired rather than try to fix it. The situation with the piston engines is in a way completely opposite. They are made up of quite a large amount of mechanisms, and the more mechanisms there are, the higher the chances that eventually one of them will fail. Besides, the constant forward and backward motion of the pistons, with an ever-changing pressure and vibrations, does not contribute to reliability and lifespan of the engine, although nowadays it is not a critical issue either. At the same time, piston engines have the advantage of being less risky in case of some mid-flight failures. They are more forgiving when pilots make small mistakes, which makes the use of automatic control systems a matter of preference rather than a law. The key advantage of piston engines is how easy they are to maintain and repair. Many of the elements in this power plant are much less demanding to the technicians working on them. They must still be treated with all due respect, but nevertheless they do allow simple repairs to be carried out in the field. Now it's time to climb up into the clouds. There is a simple fact that any school kid knows. The higher above the ground you get, the lower is the air density. Due to this fact, the differences in capabilities of different engine types separate them in a way vertically. Piston aircraft are the lowest flying machines. At low altitudes of, let's say, up to 4 kilometers, piston engines feel quite well and show their best performance. But if you get higher into the sky, they begin to experience certain problems. Air density becomes too low for them, the power decreases, and the air-fuel mixture coming into the cylinders becomes unbalanced. Meanwhile, in the turboprop engine, the air coming into the turbine already has an increased density, as it passes through a compressor. As a result, turboprop machines can fly considerably higher than piston engine planes. The optimal range of altitudes where turboprops show their best performance is between 4 and 7 kilometers. If you want to fly even higher, then you should rather use the jet engine, which can operate at higher energy intensity, allowing to lift their owners to altitudes of 10 to 12 kilometers. Here some people might object to my points, saying that this delimitation is not accurate and there are lots of exceptions. Of course they are. Piston bombers of the mid-1940s could fly at altitudes of about 10 kilometers, but their engines were fitted with lots of add-ons, turbochargers and correctors, which made the design much more complex. At the same time, 7 kilometers is not even close to being the ceiling for turboprop engines, and they can climb to up to 8 and 9 kilometers, while such monsters as the NK-12 or the European TP400 have a ceiling of just under 12 to 13 kilometers. But yet again, how many mass-produced planes with such engines could you name? And since we are here, jet engines can lift planes as high as 20 or 30 kilometers, but these are usually extremely powerful roaring machines that burst flames out of their afterburners. If you are a Mach 3 high-altitude recon plane or a Mach 3 interceptor of that recon plane, sure, it's fine. But in civil aviation, that would be like driving a Batmobile on city streets. Let's talk about kilowatts and horsepower. The differences in operating principles between these two engines lead to a different approach when you want to increase their power. In order to increase the power of a piston engine, you need to increase its size, increase the number of cylinders, and as a result, make the entire design more complex. In fact, in many cases, the more powerful piston engines are basically a combination of several less powerful engines. On the other hand, in order to increase the power of a turboprop engine, you mostly need to increase the energy density of their operation without the need to implement additional components, and this requires only a small increase in dimensions and weight. And weight is everything in aviation. For instance, before the advent of turboshaft engines, helicopters were evolving very slowly. This was due to the fact that by increasing the power of their piston engines, these would get so heavy that their carrying capacity was almost nil. Essentially, the helicopter was able to only lift itself, and even that with difficulties. However, nowadays it is not a problem. The modern turboshaft D136 engine is pretty large, but have you seen that house it carries on itself? Okay, that's helicopters and turbofshafts. Let's take a look at a couple of examples based on planes. The Pratt & Whitney PT6 turboprop on the PC-12 looks quite tiny and simple, weighing around 240 kilos and providing 1200 horsepower. Just to give you an idea, the Wright R1820 Cyclone engine that took into the skies the mighty B-17 bombers was enormous, complex, weighed about 540 kilos and delivered the same 1200 horsepower. With an increase in power, this contrast becomes even more striking. The turboprop PW150 series used on the Bombardier Q400 planes weighs 716 kilos and generates 5000 horsepower, while its piston relative, the PW R4360 Wasp Major from the B-36 bomber, is a monster that is as big as a bus, horribly complex, and weighs about 1700 kilos. It is an entire ton heavier. In addition to that, the complexity of its maintenance became legendary, and yet it delivered just 4,300 horsepower, less than the engine of this small airliner. Here you could object. You are out of your mind if you compare modern turboprops with piston engines of the World War II era. It is a rightful claim, but there are a couple of facts. First of all, most modern turboprops are not all that new. Many families of these engines date back to the 1960s. Secondly, the complexity and weight issues of piston engines are still there. Even if the Cyclones and Wasps were made nowadays, they would not differ all that much from their veteran relatives. In reality, such powerful piston aircraft engines are no longer produced. With the advent of turboprops and jet engines, this became completely pointless. On the other hand, if you don't need that much thrust and a few hundred horsepower will do, the weight factor is not all that important. This is why we have a certain division between niches. When little power is needed, piston engines are more economic, cheap, and easier to maintain. But as the necessary power grows, they become more complex, heavy, and unreliable. In such cases, the turboprops seem to be a better alternative, with their smaller dimensions, higher reliability, and an excellent thrust-to-weight ratio. The transition between engine types takes place around the 300 horsepower mark, when both options are really close in terms of their capabilities, and it all comes down to the choice of the manufacturer of each particular plane. Let's move on. How fast do we fly? The flight speed of an airplane mostly depends on two opposing factors: engine thrust on the one side and air drag on the other. If the airplane is required to fly faster, it would be better off having a more powerful engine and flying as high as possible. Obviously, the turboprop powerplant is better here. It can operate at higher altitudes, and its power-to-weight ratio will provide for a better thrust. After all, while a speed of 5 to 600 km per hour is the ultimate dream for a piston engine, it is quite an average speed for a turboprop. In fact, some military turboprop aircraft can fly at speeds of up to 800 km per hour. It is a hard thing to do, but far from impossible. However, as we lower the flight speed, the advantages of the turboprops get leveled down. So what do we have in the end? Yep, yet another division into niches. If you need to fly as fast as possible, you'll be better off with the turboprop airplanes. But at low speeds, below 200–300 km per hour, piston engines provide a better performance. Their power is sufficient and their economy is better. Everything depends on what you expect to get from the plane. Most commercial airliners, such as the Dash 8 and ATR families, whose job it is to rapidly carry passengers between airports, are fitted with turboprop engines, which give speed and flight altitude. At the same time, the majority of planes within light aviation, including such joyful machines as the Cessna 172, which carry out short flights, observation flights, and air tours, are fitted with piston engines, and they feel just fine with them. But the game continues, and the trump cards come into play. One of the bonuses of a turboprop engine is the fact that it generates a huge amount of hot air, part of which can be used for secondary functions such as anti-icing protection, cabin pressurization, and the air conditioning system. In this regard, piston engines do have some issues, and there are even times when they need to be heated. This seems to be counterintuitive. The engine itself is hot, but under certain conditions, when ambient temperatures are close to 0 degrees Celsius and the humidity level is high enough, the fuel inlet line can freeze up, causing engine malfunctions. There is no need to overplay this fact, since it doesn't happen all that often, and the aviators already know how to deal with it, but yet again, in the case of a turboprop, in order to get the compressor or the combustion chamber frozen, you'd need to be some kind of a genius of self-destruction. How can the piston engine respond to this disadvantage? Well, there is one engine attribute that is sometimes ignored, but which is nevertheless very important: their reaction speed to pilot inputs, the throttle response. When you floor it with the piston engine, it will react almost instantly, while the gas turbine engine will need some time to reach the required thrust due to a certain level of inertia of the rotating mechanisms within. In a way, this can be compared to the turbo lag you can experience in a car with a turbocharged engine. In modern engines, this lag is measured in seconds, but there are times when those seconds matter. For instance, during takeoff, an airplane with a piston engine will reach the necessary speed faster, while a similar turboprop will most probably need a longer runway. This is not a deal breaker for the heavier airplanes, such as commercial airliners, which fly calm and steady. At the same time, the possibility of instantly getting the right performance from their engines can be of great importance for the planes of general aviation, all kinds of agricultural and off-road aircraft. There are also nuances related to the part of the power plant that we can see, the propeller. The propellers that are fitted on airplanes can have pitch-altering mechanisms. This means that their blades can rotate on their axis in order to fine-tune the engine thrust without changing the rotation speed of the propeller. What's more, the blade can even get completely turned around, making the propeller push the plane back instead of pulling it forward. Something like the thrust reversal. Pretty cool. The problem is that on the piston engines, this dynamically complex mechanism increases the risk of damaging them. If air resistance is increased too fast due to pitch alteration, it can lead to the jamming of the engine, much like a stick in a wheel. At the same time, thanks to the simple dynamics of turboprop engines, such resistance will only translate to the reduction of revolutions made by the shaft. Therefore, thrust reversing with the help of the propeller is an ordinary tool for turboprops, while piston planes should approach it with caution due to the potential overloads. Alright, let's proceed to a more popular topic. An obvious question to any engine is, how much fuel does it burn? Piston engines are regarded as the most fuel-efficient power plants. And yes, since it is a piston engine, it works with petrol, which is great. However, in spite of being so similar to their surface-dwelling relatives, these engines often don't use conventional petrol, but rather specialized versions which include certain additives. Aviation gasoline, commonly known as F-gas, is more efficient, but it has its limitations, among which are economical issues and, of course, money. It is considerably more expensive than what you get at a roadside gas station. Turboprop engines are more voracious and they don't use gasoline, but rather kerosene. However, surprising as it may seem, in many cases this kerosene is cheaper than F-gas. Therefore, in terms of fuel consumption, we can call it a draw. With a similar engine performance, you should choose depending on your needs and the accessibility of one of these fuel types. Aviation, just like any other industry, is an eternal fight between technological advances and compromises. Each airplane is a complex set of problems and solutions for them, and choosing the engine is one of those problems. Today we saw the rivalry between piston and turboprop engines and learned the nuances of operating them, seemingly small but nevertheless important. And let us not forget that there are also jet and even rocket engines, let alone all their variations and all sorts of exotic machines. And each burning heart has its own upsides and downsides. This is where we'll end our motorized journey. Let me know in the comments if I forgot to mention something in this story, like and subscribe to the channel. Fast flights, cool engines under the hood, and soft landings to you.